Now we have to implement the main function to learn the decision tree, right? It's the main recursive function. So let's call it learn the tree, and it's going to receive the data, is going to receive the class name. We are going to keep one string as with all the log information of the execution for learning purposes. I mean, we will print there the entropies, the information gains, and the chosen variables, such that we can then follow up the execution and compare with the previous exercise, or with the exercise we saw in previous videos. We need to receive the root and the ID. Let me explain here why. I mean, we're using the tree library, the tree library, and this library, every time we create a node, we need to assign an ID to make sure that each node has a unique ID. And the root of the tree is going to keep two values: the name of the root and the value of the root. Why we need the value? Because recall that the algorithm, depending on the value of each of the nodes, goes into one or another edge, right? So we are going to print the value on each children node, so we can keep track of the path we are following in the tree, right? So the first thing here, we are going to accumulate in the out string the iteration of the execution. So let's say we're going to print the iteration of the ID. Is just for us to keep track of where we are in the execution. What is the node? What is the root node in this case? Okay, and let's print also the root. So the first thing is to check for the stopping criterions, right? We know that there are mainly two. So here I'm gonna check if all the labels are the same. So in this case, we need to return a leaf. To check that, we need to see if, again, the unique values of the labels is just one, then it means that all the labels are the same. So here we create the tree. Recall we are using the tree leaf package. Every time we return something from this function, we need to return a tree. If we return a leaf, it's going to be a tree such that we can paste that tree with the general tree we are building recursively, and then we will end up with the whole model, right? So this is why every time we need to create a tree, in this case, we have to create a node. We need to provide this with the name of the node. So in this case, the name of the node is going to be exactly the label that is repeated across all the rows here. So let's say like the values. And also we need to keep track of the parent, because recall that, for example, in this case, we are creating a leaf node down the node root, but we don't know which value actually is taking the root node. So here, let's add some information to the string, right? We are going to print this root name. Recall that the root in this case is just the parent of this particular leaf node, and the value. Besides the name, we need to provide with the ID. So let's say that the ID of this node is the ID we receive. So here you can see that now the ID that we are receiving as an argument in the function is the corresponding ID we should use for the node we are creating. So this is why we are grabbing exactly that ID and assigning it to the node we are building or creating from scratch here for the leaf node in particular. Now we need to keep record of what's going on here. So all the classes are the same, and we create a leaf equal to something, which is the name of the class, basically. Let's add some spaces. We can do the 50 dashes and skip one line. Okay, and we have to return, right? So because we are in the stopping criteria, so what we have to return here, the tree we just built, which is basically one leaf, and we need to return the next available ID always, which is the current one plus one, the last we used plus one, and then we need to return the current version of our string with the execution information. Okay, so that's the first stopping criterion. Now let's check the second one. So in case that all the rows are the same, for this we have created our function, right? So if we have the same data of the current version of the dataset and the class name, then we need to return again a leaf. But what leaf? We need to calculate the most frequent class among the remaining rows, right? Recall that in this case, all the rows are the same in the variables, but not necessarily in the class. So here, so let's capture again the possible values that the class can take. And let's use this variable to choose the maximum amount of votes. Okay, so the prediction, recall that in cases when we have different class values with the same frequency, we must choose randomly. Okay, so let's start by initializing the prediction in a random choice, in a random value of the class, right? It's just an initialization. So then every time we have any class value with more votes, is going to be updated. But in case all of them are the same, it's going to be a random prediction, which is fine. So for each of the values, we're going to calculate the number of votes. So we need to select the rows where the class is equal to the element, and then we just need to check if this number of votes is greater than the current maximum number of votes. So if that happens, we just update our maximum number of votes and set our prediction with the current maximum, which is this element in particular. Okay, so here we basically have already the prediction, right? So we have to build now the tree we are going to return. In this case, again, we build a tree, we create a node. The name of this node will be the prediction, right? Because it's a leaf node. And we are going to add again the information of the root of the parent. So we know which arm of the parent we are following in the path. Here again will be root of name and value. And we need to provide also with the ID, which is again the ID we got as an argument. And let's register this in our execution string. So we are going to accumulate now this message. All the rows have the same value, and we added a leaf with something here, which is the prediction. And let's repeat this situation. So again, here we are going to return, add these spaces and return the tree with the string and with the next ID. Great, so since that we are fine, we have the two stopping criterion. Now we need to assume here that none of these criterions hold. It means that now we need to choose the variable with the highest information gain. So else we didn't fall into any of the previous cases. Let's initialize our information gain in minus. So let's check if we are in the case where there is just one remaining variable. So then we avoid to go over the process. If there is just one remaining variable, we need to return it, right? So we need to discard or exclude the class name. Then we know that the winner is going to be actually this. That variable. And in case it does not happen, we start calculating everything, right? First we need to calculate the entropy. So let's print this to keep a record of this process. Right, we're just printing the entropy as we usually do in the slides before. Now we need to extract. Let's extract a list of variables. Sorry, let's do the following here. So we can save some calculus. So okay, that's much better, right? So we extract here the list of variables, and then we check if the len is just 1. We're going to just return as a winner the only one, right? We're going to have to use the toList function from pandas. Okay, so now for var list of vars, we calculate the information gain of this var. We need to provide the class column. So if gain is greater than the maximum information gain, then we set this information gain, sorry, with this value, and the winner is going to be this variable. Let's say we have two different variables with the same information gain. With this process, we will always choose the first one we find, right? Because it's not going to be updating in this part, because it's not going to this update only when we find a higher information gain. One idea is to shuffle here the list of variables, right? But because if we shuffle this, we make sure that every time we pass here, not necessarily the first variable with the highest information gain is going to win, right? In case one or two or more variables have the same information gain. And actually this happens in our data set. Recall from the previous video that in the last step there we found two variables with the same information gain, and we choose randomly, right? Okay, so now we need to check the values of the winner. So let's say that at this point we already have the winner, right? The winner variable. Now we need to obtain the possible values of the winner, the data winner. Sorry, let's add some annotations here. We can keep track of every calculus of information gain we are doing during the process. So we're gonna say here the information gain of the variable var. Let's add one extra line, and the gain, right? So we can keep track and then take a look and test if we found all the middle or the internal information gains are matching the ones we had in the previous video in the slides. Let's also keep track here of the best variable. So we know what we have chosen in every step of the tree construction. Let's add some space as we did here. Okay, now we must create the subtables, right? I mean, we must instantiate the data and reducing it to a smaller table. And create the call, the recursive call. We must create the tree again. We are going to save the ID of the winner node. We are going to increment the ID, because here we are going to loop over the values that the current node can take. Okay, so let's do it here better. So we're gonna create a node with the name of the winner and with the ID of the winner. We are going to loop over all the values that the winner can take, and we are going to create the subtrees recursively. So let's instantiate the data. It means that now we need to select the table where the variable winner equals that value. Let's remove that column because we know that winner is the same value in all the rows. So now let's create the subtree, the ID and the string. This is what our function returns, right? So we are calling here recursively our own function, which is called the learn decision tree. Now with the new data, right? The class name is the same. The out string, we are passing it the current version of the string with all the execution information, right? So this function is going to return an updated version of the same string. We need to pass here the root. We know that the root has two fields, name and the value. So the name is the winner name, and the value is val, right? It's the value we are currently in this loop. And finally, the ID, which is the incremented version of the previous ID, right? Recall that here we use the ID that this function receives in the argument for the winner. We increment it in 1 and we pass it to the creation of the subtree. So after we have this subtree, we basically need to link it as a child node of the winner. So the treelib library has a function called paste, where we just literally paste the substring, or I mean the subtree, under the parent, in this case which is winner, right? Here I pass the ID of the parent, in this case the winner, and I pass the subtree. This is going to create a tree where we have the winner as a root node, and under the winner we have the subtree as a child, and we just return the tree, the incremented ID, and the string. So this is why here the ID is not being incremented again, because we know that this is returning an incremented version of this ID and is using the last version here. So this is why we increment it first, we use it here, we return it incremented, and so on. Okay, so this is the main function. So let's see what happens. We have some errors. There is a syntax problem in this part. Yeah, we have an indexing problem here. Okay, I think this error is because forgot to do something here, which we need to make sure that these are transformed into numpy arrays, because they come from a pandas data frame. There we go. Cool. So you can see here, let's actually print out the string also. Great. So you can see here that this is the same tree we have built in the previous video. We can improve a little bit the printing of here, because we need to see the name of the parent node, the value of the parent node, and this could be improved in this place here when we create a node. When we are in the actual root, it means that the root name is empty. Okay, here means that there is not the root, right? So we need to add some information here. We know that it's not the root because when we call this recursive function for the first time, we put into the root parameters an empty string, and then recursively those roots start getting the name of and the values of the internal nodes. Here I'm gonna print the value of the parent node. Let's actually do the following. So when it is an internal node, we are going to print the value of the parent, so we know from which branch we came to the current node. So I need to add here the ID. Okay, here we go. So here you can see the name of the value of the parent, right? So here it tells us this is the edge where live with parents equals no, and so on. We can improve this here also in the leaves, in this part. Now much better, right? So these are the leaves, and in the leaves now we also know what is the value that the parent variable took. So this is the weather, for example, we live with parents is yes. Then we got the economical situation where the weather is sunny. So you can check that tree and compare it with the one we had in the previous slides. Now we can see the execution of the algorithm, right? These are all the information gains and entropies. You can check the numbers with the example we saw in the slides.